Hello and welcome to the Week 5 Math 2414 review. In this one, we'll be talking about improper integrals, some arc length, and then we'll get into some surface area of revolution. So first off, improper integrals. In general, improper integrals are integrals that tend to just kind of have kind of wacky areas. So what that means is most frequently, you'll either be integrating where one or both of your limits are infinity, like this, and we call these ones type 1. Or you'll usually be integrating over some kind of discontinuity. It's most frequently an asymptote. And we call these ones type 2. So usually we have a couple of different methods for solving these improper integrals, but most frequently all we're going to do is we're going to take the point where a problem arises. So in this, for type 1 integrals, it's the infinite point. For type 2 integrals, it's where we have our discontinuity, and we're just going to rewrite it as a limit. So for example, we'll do the most classic improper integral there is, the integral from 0 to infinity of e to the negative x. Well, we can't actually plug in infinity. Infinity isn't a number. So what we'll do is we'll rewrite it as the limit as b goes to infinity. And now we have the integral from 0 to some number b. Now e to the negative x is a pretty simple integral. It is just negative e to the negative x. Of course, I forgot my limit statement, so I'm going to put that down first. Negative e to the negative x, evaluated at 0 and b. And here we have minus e to the 0 is negative 1, so minus negative 1 gets us plus 1. And plugging in b as b goes to infinity, we have e to the negative infinity. E to the negative infinity is 0. 0 plus 1 is, of course, 1. Now, for a slightly more complicated example, let's say we were integrating from 2 to infinity of 1 over x squared minus 1. Well, first off, in order to actually perform our integral, we're going to need to do partial fraction decomposition. So here we have a over x plus 1 plus b over x minus 1 equals to 1 over x squared minus 1. So a times x minus 1 plus b times x plus 1 gets us 1. Now if we plug in x equals to positive 1, we have 2b is equal to 1, so b is equal to 1/2. And if we plug in x is equal to minus 1, we have negative 2a is equal to 1, so a is equal to minus 1. Well, now we have the integral from 2 to infinity of minus 1/2 over x plus 1 plus 1/2 over x minus 1. Again, we're going to want to rewrite this as a limit. Here, the point that's giving us an issue is our upper limit again, which is infinity. So we have the limit as b goes to infinity of the integral from 2 to b of minus 1/2 over x plus 1 plus 1/2 over x plus 1. Now I'm just going to pull out my 1/2 right now, and then I have the limit as b goes to infinity. I can go ahead and integrate as well. The integral of negative 1 over x plus 1 is negative natural log of x plus 1. The integral of 1 over x plus 1, oh shoot, this should be a minus 1. X minus 1 there. And then the integral of 1 over x minus 1 is the natural log of x minus 1. And I'm going from 2 up until b. Now I'm actually going to recombine my natural logs using some log rules. Here I have the natural log of x minus 1 minus the natural log of x plus 1. I can rewrite that as a single log, as so. Okay. So now I can go ahead and plug in my limits. If I let b go to infinity, this inside portion is a balanced rational equation. So the limit as b goes to infinity of b minus 1 over b plus 1 is 1. The natural log of 1 is, of course, 0. So I have the natural log of 1, which is 0, minus the natural log of the absolute value of 2 minus 1 is 1. The absolute value of 2 plus 1 is 3. So I end up with negative 1/2 times the natural log of 1 over 3. And if I wanted to simplify that further, I can write 1/3 as 3 to the negative first, and then bring that power down out front as a coefficient. Questions?
So just to be sure, the way you what you did with that element of x minus 1 over x plus 1 when you plugged in b was you did L'Hospital's rule, right?
In this case, I didn't need to do L'Hospital's rule, although that is something that would work. I just said that x minus 1 over x plus 1, if I take the limit as x goes to infinity, this is a balanced one. So I look at the coefficient of the largest terms, which is 1 over 1.
So you basically did L'Hospital's
rule. It's a slightly different method.
Okay.
If we did L'Hopital's rule, we would need to take the derivative of the top, which is 1, and the derivative of the bottom, which is 1, and it comes out to the exact same answer because it's just two approaches of solving the same problem.
Okay.
But is that it?
I think so.
Perfect. Practice problem. And we'll get to some type 2 integrals in a little bit. All right, I'll give you a couple minutes to work through that. All right, let's go ahead and go over this one. So first off, we're going to need to rewrite it as a limit. You'll notice that for x larger than 0, the denominator is always positive, so we don't really have to worry about it ever being 0. And now we can just go ahead and apply u substitution. So then we have the limit as b goes to infinity of technically, I'm just going to solve my integral first and then substitute in my limit so that I don't have to change my bounds of integration. So we have the integral of x squared over 1 plus x cubed. It's just the integral of du over u, which is of course the natural log of u plus. So our integral then becomes the limit as b goes to infinity of the natural log of 1 plus x cubed. Since we have a definite integral or a bounded integral, we don't need to include our plus. Now, you'll notice when we let b tend to infinity, we have the natural log of infinity, which is infinity, so we say this integral diverges. Okay. Now let's take a look at some type 2 integrals. So in a lot of situations, we have type 2 integrals, meaning we're integrating near some kind of asymptote. So for a quick example, let's say we are integrating from 0 to 2 of 1 over x dx. In this case, I'm going to need to rewrite the point of discontinuity. In this case, I have an asymptote at 0. So I replace my asymptote with some kind of limit statement. You'll notice in this case, I'm only approaching this point from the positive direction, so I'm specifying that in my limit. Now I can go ahead and perform my integration. So I'm taking the natural log of x. Since x is always positive, I'm ignoring my absolute value bars. And I'm going from a up until 2. This is the natural log of 2 minus the natural log of 0 from the right. This approaches negative infinity. Yeah, sorry. In other words, if we sketch out a quick graph of natural log, as natural log goes to 0 from the positive direction, it goes to negative infinity down here. And this is, of course, infinite, so this diverges as well. For a slightly more complicated example, let's say we were doing the integral from -1. Actually, we'll do from -2. From -2 up until +2 of x divided by x plus 1 squared.
So when you say something diverges, does that just mean that there's technically not an exact number beneath the line?
It means we have an infinite area.
Okay.
So we have an infinite area. That's what divergence means.
Okay.
And we can't really assign an exact number to it, even in terms of infinities, because if you take infinity and you add 1, it's still just infinity, right? So it kind of messes with things a bit. All right. Now, here we go. Here, you'll notice we have a discontinuity at x equals -1. That's where we have a vertical asymptote. So in this case, we actually want to split this up into 2 separate integrals. Like so. Because we have our asymptote at x equals to -1. Now, I'm just going to focus on this portion from here on out. And then I'll return to this portion if I need to later. Sound good? So performing this integral, again, I need to rewrite my point of discontinuity as a limit. So I'm going to take that lower limit, say that as a approaches -1, again from the positive direction of the integral from a to 2 of x over x plus 1 squared, well, then I can perform a u substitution. And this becomes, or I guess the indefinite integral x over x plus 1 squared then becomes the integral of u minus 1 over u squared, which is the integral of 1 over u minus 1 over u squared, which is the natural log of u plus 1 over u, which means this integral becomes the limit as a goes to -1 from the positive direction of the natural log of x plus 1 plus 1 over x plus 1, evaluated at a and at 2. Now, the issue here is when I let a approach -1, here this approaches the natural log of 0, and then approaching the natural log of 0 from the positive direction, again, is -infinity. So this portion gives us -infinity, and that automatically tells us that our whole integral is going to diverge. So an important thing is we can't cancel out infinities. It's just not allowed, because you can, if you could cancel out infinities, technically you could make it so that you could get whatever number you wanted. And what I mean by that is, if I had some kind of vertical asymptote, let's say like this, actually, something like this, well, I could take the integral from here and go onwards, and if this were infinity, and I said I wanted to cancel it out with an integral from here to here, well, if I cut off this little portion of this one, this is a finite area, which means that this area still has to be infinite, which means because it's infinite and we're saying we can cancel, it would have to cancel with this infinity. But then I'm left with this left over. But then I could just change that amount however I wanted and end up with whichever number I wanted. So that's kind of an intuition behind why we aren't allowed to cancel infinities. It would let us get to whatever number we want. So because of that, it just has to diverge. Any questions?
Just seems like discrete math.
Math is all connected, you know. All right, practice problem. And I'll give you a couple minutes to work through that. All right, let's go over this problem. So first off, we notice that sine of 0 is 0. That's where we get our discontinuity. So we're going to have to rewrite this as a limit. And again, in this case, simple u substitution will suffice. So this becomes the integral now of 1 over square root of u, which is the integral of u to the minus 1/2, which we can just use the power rule on, which becomes 2u to the 1/2, or 2 square root u. Which means in our case, we end up with the limit as a goes to 0 from the positive side of the square root of sine theta from a up until pi over 2. Now, plugging in our limits, sine of pi over 2 is 1, the square root of 1 is 1. We subtract our lower limit. The limit as theta goes to 0 of sine is sine of 0. We can just use direct substitution. Sine of 0 is 0. And we end up with 1. Of course, I forgot to put my 2 in there. So going back and putting my 2 in there now, well, that gets us a 2 minus 0 instead. So 2 minus 0 is 2. Apologies for the small mistake. But overall, we get a final answer of 2. Any questions? Perfect.
Although, actually, yes, I do have one question.
Yep.
We plugged our A into our U. Would we just like write our value? Like if we didn't sub U back in, would we just write like sine of A?
Yeah, so you could do, I mean, in this case, it kind of messes up things up a little bit, or it might make things a little more complicated because you want to preserve this directionality. So you would have to consider, I guess, kind of when I make that substitution, am I not going to make sure that somehow I'm approaching 0 from the left side instead of the right side this time? It just makes things a little more difficult in my opinion. So if you solve the indefinite integral first and then just don't bother changing your bounds, that might be a little easier in these situations. Good question though. All right, ready? Perfect. That's enough of indefinite integrals. We got a lot to cover, so we'll talk about Arclength now. Now, do you happen to remember your Arclength equation?
Square root of 1 plus dx over dy. No, wait, dy over dx squared.
Right.
Dx.
So our arc length is the integral from some start point to some end point of 1 plus r derivative squared. And you might see that written as the integral from a to b square root 1 plus dy dx squared. Or if you are, actually, we'll just leave it at that for now. So we'll start with a quick example. I'm not going to go through the whole derivation of this formula. It's in your textbook if you're interested. But frankly, we just don't have time today, so we'll just start off with an example. Let's say we have f of x is equal to the square root of 1 minus x squared. And we're interested in finding the arc length on the interval from -1 to 1. All right. Now, do you happen to know what shape this is?
X squared tells me parabola, but the square root tells me something different.
All right. So we'll just start. Y is equal to the square root of 1 minus x squared, right? So y squared is equal to 1 minus x squared.
Okay. Oh, so it's a sideways parabola.
So x squared plus y squared equals 1. Right, it's a circle, except in this case, y specifically has to be positive, so we just have the top half of the circle. And what's the circle's radius?
1.
Right, the circle's radius is going to be 1. So we have the top half of a circle of radius 1. Or in other words, the arc length should be half of the circumference of a circle of radius 1, right?
I honestly don't even understand what the Arclength is.
So we're looking for the length of this curve. That's what the arc length gives us.
So we're trying to straighten that curve out.
We're trying to straighten that curve out and see how long it is.
Okay.
Now we know the circumference of a circle, right? It's 2 pi times the radius. So when radius is 1, our circumference is 2 pi, right? But we only have half of a circle. So in this case, we can kind of know that our arc length should come out to be pi. So let's see if our equation actually matches that. Using our equation, we're just kind of going to plug in. We know that it starts at -1 and ends at +1. We also know our derivative. We can just take that. Using the chain rule, we get 1 over 2 square root 1 minus x squared times the derivative of the inside is -2x, which then becomes -x over square root 1 minus x squared, right? Okay, so then we have 1 plus -x over square root 1 minus x squared, right?
Yeah.
This is my 1 plus my derivative squared. Then I have 1 plus -x squared is x squared, and square root 1 minus x squared is 1 minus x squared, right? So now I'm going to combine everything on the inside. My common denominator is going to be 1 minus x squared. So I can rewrite this 1 as a 1 minus x squared divided by 1 minus x squared, right? So then this becomes the integral from -1 to 1 of the square root 1 minus x squared plus x squared is simply 1. And on the bottom, I have 1 minus x squared. Right? Okay. Which means this is the integral from -1 up till +1 of 1 divided by the square root of 1 minus x squared.
Oh wait, you lit me straight.
What?
You lit me straight. What happened to x squared?
So these x squareds,
Uh,
if I add my numerators, I have 1 minus x squared plus x squared. And -x squared plus x squared just cancels.
okay. I was thinking that 1 minus x squared would just cancel with the 1 minus x squared of the other denominator.
Oh, but when we're adding fractions that have the same denominator, they keep their denominator, right? You just leave the denominator alone. Okay, but does it make sense how I get to here now?
Yep.
All right, do you recognize that integral?
Is it sine?
Not sine,
Arc sine.
arc sine, right. So this is our arc sine integral. And we're evaluating it at -1 and +1. So now we think, what angle, when we take the sine of it, do we get 1?
Pi over 2.
Right, right? And what angle, when we take the sine of it, do we get -1?
Simply pi fourths.
It would be on the other side of the unit circle, right?
You have pi.
So here our sine value is at pi over 2, and that gives us a y value of 1. Down
3
here,
pi halves is what I meant. 3 pi halves is what I meant.
right, 3 pi halves, but specifically our arc sine function is only going to give us answers from -pi over 2 to +pi over 2.
Oh,
So -pi over 2 will get us a -1. So we have -pi over 2 there. And this is pi over 2 plus pi over 2, which is, of course, pi. And that matches exactly what we said it should be. Pretty neat, huh? Admit it, you like it.
no.
All right, time for some practice problems, unless you have any questions. Okay. Find the length of all right, and I'll give you a couple of minutes to work through All right, let's go over this problem. So first off, we can identify our bounds, 0 and 1/2. We can also find our derivative. Perfect. So now we just kind of plug all this into our formula. We have the square root of 1 plus negative 2x over 1 minus x squared squared. Now this becomes the integral from 0 to 1/2 of the square root of, here we can actually rewrite our 1 as 1 minus x squared squared, again over 1 minus x squared squared. And here we have plus 4x squared over 1 minus x squared squared. This gives us the square root of, on top, if I go ahead and FOIL out my 1 minus x squared squared, this is 1 minus 2x squared plus x to the 4th. And then I also have plus 4x squared. And on the denominator, I have 1 minus x squared squared. Now my squared and my square root here are going to cancel. So on the bottom, I just have 1 minus x squared. And in the numerator, I'm going to combine my like terms, which are the negative 2x squared and the plus 4x squared. This gives me the square root of 1 plus 2x squared plus x to the 4th, which, if you're paying close attention, you'll actually recognize as a perfect square. So I'm going to factor the top into a 1 plus x squared squared. And again, my squared and my square root are going to cancel. Any questions as to how I got here? Nope? Okay. Well, now I'm going to rewrite this as, I can write 1 plus x squared is equivalent to, let's see, how did I do this? All right, I am actually going to pull out a negative first. So I have 1 plus x squared, and then I pull the negative out from the denominator, and this is an x squared minus 1. Now I can write x squared plus 1, which is my numerator, as x squared minus 1 plus 2, right? Which means I can rewrite my integral, still have my negative out front, as x squared minus 1 over x squared minus 1 plus 2 over x squared minus 1. Right?
Did you use the like 2a squared, 2ab, b squared?
Yeah.
Okay.
So this is a squared, this is b squared, and then this is 2 times a times 1. And then I just factor it. Okay. Am I good to keep going? All right. This part, of course, simplifies down to 1. So I can rewrite my integral as negative integral 0 to 1/2 of 1 plus 2 over x squared minus 1. Now, 2 over x squared minus 1, do you happen to remember? Well, actually, this is going to be another partial fraction decomposition. So I can actually go ahead and solve my first integral. This is just negative x from 0 to 1/2. I put my negative back in. And here I have plus the integral from 0 to 1/2 of negative 2 over x squared minus 1.
Do you not have to distribute that negative?
What do you mean this? So I put this negative back in here, right?
Right. So shouldn't it be oh, I'm sorry. I was expecting the negative to appear in front of the integral sign.
No. I distributed it back into my integral. It's really personal preference. You can do it either way. But now what we have is a partial fraction decomposition where a times x plus 1 plus b times x minus 1 should equal to negative 2. So if we let x equal to -1, then we have -2b is equal to -2, so we see that b is equal to 1. And looking at just the x terms, we have bx plus ax is equal to 0, so a is -b, so a is -1. That should be a -1. Make sense? I know I'm running through this kind of quickly, but all right. Now evaluating this, we have -1/2 minus 0 is -1/2. Here we have the integral from 0 to 1/2 of -1 over x minus 1 plus 1 over x plus 1. And this becomes the plus negative natural log of the absolute value of x minus 1. And in this case, your absolute value bars are actually very important. Plus the natural log of the absolute value of x plus 1. Evaluated at 0 and 1/2. So when we plug in 1/2, we have the natural log of 1/2 minus 1 is -1/2. The absolute value of -1/2 is 1, positive 1/2. And then we have plus the natural log of this times 3/2 minus the natural log of 0 minus 1 is -1 plus the natural log of 0 plus 1 is 1 again. So these are both 0. We can ignore them. And what we're left with is -1/2 plus the natural log of 3/2 minus the natural log of 1/2. And remember, difference of logs means we can take them and rewrite them as a quotient. Three halves divided by 1/2 is 3. And we're left with 1/2, -1/2 plus the natural log of 3 as our argument. Questions?
I get where you got L of 3, but where'd the -1/2 come from? Like with the plus sign.
Right here?
Yeah.
So this came from our first portion of our integral. So you'll remember way back up here, what we did is we rewrite 1 plus x squared as x squared minus 1 plus 2. And what this does is when we rewrite our integral 1 plus x squared as x squared minus 1 plus 2, it lets us get a single 1 term here, but we still have to integrate that 1, and this becomes a -x if we put our negative sign back in, which gets us our -1/2.
Oh, okay. I see. That because I was looking over here and I didn't see that x, and that's why I was confused where you were putting.
Yeah, so that's where it came in. Make sense?
Yes. Long problems are just tough because I have a short attention span.
Fair. Okay. We probably have enough time for about one more good problem. The question is, how much of surface of revolution have you covered so far?
Just like one problem. We haven't gotten in like the 2 pi and stuff.
Oh, okay. In that case, we're just going to do one more Arclength problem, and I think call it good from there. In this case, another practice problem. Find the Arclength of y is equal to x cubed over 3 plus 1 over 4x from 1 up to some number s. In other words, I want you to find the Arclength from 1 to s, and then fill in the rest of the Arclength function yourself. And I'll give you a couple of minutes to work through that. let's go over this one. So first off, we need to find our derivative. In this case, it's pretty simple. The derivative of x cubed over 3 is just x squared. And then the derivative of 1 over 4x is negative 1 over 4x squared. So we can just do x squared minus 1 over 4x squared. And here we have the square root of 1 plus x squared minus 1 over 4x squared, all squared. Now we're going to go ahead and FOIL this out. 1 plus x squared gets us x to the 4th. Here we have minus x squared over 4x squared minus x squared over 4x squared plus 1 over 16x to the 4th. You'll notice that both of these terms are each 1/4. So I'll write that. 1 plus x to the 4th minus 1/4 minus 1/4 is minus 1/2. And now I can combine my 1 with my negative 1/2. And I have x to the 4th, not x squared, x to the 4th plus 1/2 plus 1 over 16x to the 4th. Now, several of you have probably already seen this trick, but basically what you'll notice is this term was perfectly factored, is a perfect square from here. Now, if we have something of the form a minus b and we square it, this gets us a squared minus 2ab plus b squared. And if we have something instead of the form a plus b squared, this gets us a squared plus 2ab plus b squared. Now, the only difference between these two things is the sign on the 2ab term. So if you look at the squared expansion of this, our 2ab term is minus 1/2. If we look over here, our 2ab term is plus 1/2. And our a squared and b squared terms are the same, which tells us that because we have an a minus b perfect square here for the negative version, for the positive version, we should have an a plus b version. And our a plus b version in this case, our a was x squared, our b was 1 over 4x squared. So we can factor this perfectly. And that allows us to cancel our square root. And then simply integrating, we get 1/3 x cubed minus 1 over 4x, correct? Yes. From 1 up until s, plugging in the limits, we get 1/3 s cubed minus 1 over 4s minus 1/3 minus 1/4. 1/3 minus 1/4 is 1/12. So our final answer is 1/3 over 3s cubed minus 1 over 4s minus 1/12. And this is an arc length that depends on s. And when we have something like this, we often call it the arc length function, because now it allows us to express our arc length in terms of a given integral. So if I said, well, what's the arc length from 1 up until 10? Because I solved it in terms of s, now I can simply take 10 and plug it in here, and I have my arc length without having to do my integral. I can do this for any x value that I wanted, as long as I start doing it. Any questions? And again, this is called the arc length function. All right, well, if there are no other questions, we'll go ahead and call it for today. So thank you for coming, and as always, have a nice week.